the season for cool candle combustion chemistry. So there's a lot of cool science happening inside a candle. So we're talking everything from physical changes, the wax melting, vaporizing, so turning into a gas, and then chemical changes, that gaseous wax molecules reacting with oxygen in the combustion reaction, which is like this complete oxidation where you're taking a hydrocarbon, so something with carbons and hydrogens, like these wax molecules, and you're breaking them down into carbon dioxide and water. But there's a lot more going on inside a candle in terms of like making soot, which are like partial combustion products. That's where you get the smell and stuff. What about the color? So some of that's coming from incandescence. Basically, these soot molecules are getting so hot that they're giving off this energy that's so energetic that we can see it. And then the bluer color, well, that's coming from chemifluorescence. So we talked a lot about like fluorescent or chemiluminescence. We talked about a lot about fluorescence, which is where a molecule absorbs light of one wavelength, and that like excites an electron, and that electron falls back and it lets off light. Well, if you get that absorption, that excitation energy from like a chemical reaction, we call it chemiluminescence. And so that's what's happening, and that light's more energetic, so that's why you see the blue. What about the shape? So basically, hotter things are going to have more energy to move, so they will move. And you end up with this net, whereas colder things aren't going to have as much energy to move, so they won't move as much. So you end up with this net movement of the hot air to the cold air, and this is convection. This convection is going to generate this flame shape. It's like teardrop shape. Okay, what about the wick? So the wick, basically, in the heat is important for helping melt the wax, and for that helping in the melt and doing like the pyrolysis, so the breaking down the bigger chunks into like smaller carbon chunks, which is where like the soot and stuff comes from. But when you heat the wax and it becomes a liquid, now you want to get that liquid in contact with the air, which is where the oxygen is. So the wick is going to help through capillary action wick the liquid up towards the oxygen. So it's going to basically, the wax is going to absorb into the twine of the wick, and then capillary action, so it's going to get attracted to the twine molecules, and that'll kind of like drag it up. And as it's getting dragged up, now you have more of the like solid wax available to be heated, and you have this liquid wax getting up into where it can more easily contact the air. See, you can light the smoke. So this is actually something cool I learned from a Bozeman Science video, is that when you have like those trick candles, those like party candles where you think you're blowing it out and you're not really, they have those candles, they have the twine that's like wrapped with metal. And so this way, if you when you blow out the candle, the metal is still going to keep enough of the heat that it is going to be able to heat that smoke, heat that vapor enough to catch it on fire. And these candles have it like twisted around, so there's kind of like regions where it's like wick and regions where it's like metal, so it's like sparkling and crackling effect and stuff. So pretty cool. Let's look in some more detail.
So we'll get more into the details of all of this as we go on, but I just want to give you a sense of where we're going. So, but the basic overall reaction is we have this hydrocarbon, so this chain of carbons and hydrogens, and it's going to get broken down as far as it can get broken down, basically, into water and carbon dioxide. And this reaction is highly exergonic, which means that it gives off energy, and this energy is going to be given off in the form of heat and light. We're also going to have incomplete breakdown products, and that's going to give us our soot and stuff. But let's take a look at what this wax is. So the wax, for our fuels are going to be the wax and the oxygen. That's our input. Those are our reagents, basically. And then our products are going to be the water and the CO2 with the heat and the light. So basically a wax, there's not really like a set defined definition of a wax, but it's typically like a hydrocarbon. And so a hydrocarbon has carbons and hydrogens linked together. A lot of waxes have what we call these ester groups. And these ester groups are basically when you take like a fatty acid and an alcohol, so something with the carboxylic, this like you have a hydrocarbon chain with this carboxylic head and a hydrocarbon chain, like a long chain alcohol with this OH group, and then these combine and they give you this thing where you have a double bond so to an oxygen, so a carbonyl group next to an oxygen, so this is called an ester group. And so this is an example of an ester. And so a lot of waxes have esters, but not all waxes do. For example, paraffin wax, which is like the main wax making up a lot of candles and stuff, is actually just a mix of a lot of different hydrocarbon chains. So what is so special about these hydrocarbon chains? Well, basically nothing. That's kind of the point. They're like super duper boring. And so hydrocarbon chains are basically like the skeleton of organic molecules. And so normally we think about all the fun stuff happening in organic molecules. So like in these hydrocarbon-based molecules, it's happening from like specific functional groups. So basically where you replace some of the hydrogens with more interesting looking stuff, like those carboxylic acids and alcohols, as we saw, could react before to form those esters. But hydrocarbon is super, super duper boring. And so basically all it can do is combust, but it can combust and that can give us candle stuff. But the reason why it's so boring is so basically all of these carbons and hydrogens and oxygens, all of these different things, these are all atoms. And so atoms join up to form molecules by sharing pairs of these subatomic particles called electrons. And when they share these pairs, sometimes they don't really share fairly. And so for example, oxygen, it really hogs when it shares a pair. And so we call it electronegative. And this makes, this is why, like, for example, water is what we call polar, because this oxygen stealing the electrons, and this is making it partly negative, and the hydrogens are left without as much electrons, so they're partly positive. So basically, you can get molecules out of like these more reactive parts because things don't really like being charged, and so they want to find something with like an opposite charge and that sort of thing. So if you have things like this, you can have things be more interesting and have reactions. But if you have just like a hydrocarbon, the hydrogen and the carbons share pretty evenly, so you get something pretty boring. When you get something pretty boring, well, the water doesn't really want to hang out with it, and so you get this thing called the hydrophobic effect, where basically the water is going to exclude those things because they're really boring, and so the water is going to gang up around it and form these networks around it. And that's still like kind of force the hydrophobic things, so the water excluded things together, whereas the hydrophilic things, so things water likes, can be like near the water, and the water can hang out with them. And so this effect has like an entropically driven, so basically the hydrophobic things, because if you squunch them together, then that makes less of the water have to be involved in forming these like caves or like clathrates around those hydrophobic things. So basically you get this hydrophobic effect where the hydrophobic things kind of cluster together. And this is why like oil and water don't mix and stuff. And this is why wax can be used to like coat leaves and stuff. And so you get like those droplets of water on top of the leaves instead of the water just like, I don't know, dissolving the leaves or something. I don't know what would, but anyway. And so we call these like hydrocarbon based molecules lipids. And so waxes are a form of lipids, and that waxiness comes from that hydrophobic effects, like that waxy, like, you know, that like the water won't, like the water repellent or whatever, it's from that hydrophobic effect. So there are some cool things about like waxes, but they can't undergo reactions really because they don't have, other than combustion, because they don't have any of those like special functional groups or anything where there's like unfair sharing or that sort of thing, because the carbon and the hydrogen are sharing pretty fairly. So you don't have any sort of like polarity, you don't have anything really interesting. There's nothing really to attack. But if you give something, even a hydrocarbon, if you give it enough energy, it'll break apart. And so we have to put in energy to break these bonds, but then we can also get energy back when they're broken. And so basically, the net effect, we can think about how like a free energy change. So if a reaction is, we can talk about a reaction, the reaction when we have this combustion, it's going to be exothermic and exergonic. So it's exergonic, it's going to release energy, and it's exothermic, it's going to release heat. And this is going to be evidence why your candle like gets hot and why it gives off light. But you'll see that different parts of the candle will have different like heats. And this is in part because you have to give in heat in order to initially break those bonds. So that actually is endergonic. So it takes energy. But then the net effect is you're breaking down these products into these stabler products with more entropy and all of this stuff. And so more entropy is just like randomness or disorder. And so you're getting these like more favorable products. And so overall you have an exogonic and exothermic reaction where you're giving off energy and you're giving off heat. But different zones of the candle will have different heats because, for example, when the wax is melting, that also requires taking energy. And we need to melt that wax in order to get it to react. So basically, when we're melting the wax and then vaporizing it, so turning it from a solid to a liquid to a gas, these are physical changes. So basically the molecules, even though the hydrocarbons are like super duper boring, they can actually like stick to one another through just like kind of chance random interactions. So these carbons and the hydrogens are sharing really fairly, but if they like, because their electrons are like in these electron clouds rather than like fixed in a set place, these clouds can kind of get like temporarily like polarized. So you can have like they're just like randomly happen to shift and be one area or whatever. And so you can get these clouds shifting and kind of syncing up, and then you can get them kind of sticking together. And so you can get, these molecules can get stuck to one another, but if you give them enough energy, they can break free because they don't really like being stuck to one another. They'd rather be free, but they don't have enough energy to be free. But if you give them energy in the form of heat, so heat's a form of energy, if you give them energy, then they can wiggle enough to get free from one another. And when they break free, then they can go from being a solid to a liquid and from a liquid to a gas. And we need them to be a gas because that's where they're going to interact with the oxygen gas. But these are all physical changes. So here we're not changing the properties of, we're not changing like the chemical composition of the wax. We're not like breaking it down. But we often when it is in the gas form, it has been broken down already partway by what we call pyrolysis, which is basically where you just have the breakdown is happening because of heat. So pyrolysis is basically like this heat-induced splitting. So if you put in enough energy, you can break these bonds, even if you don't have like enough oxygen available to take things, oxidize things all the way into forming water and CO2. You can think of it kind of like how our body has like enzymes or like these protein reaction helpers that'll actually cut up big molecules before they get further broken down in our like metabolism and stuff. So the pyrolysis, this heat can kind of break down these products into these wax chains into shorter chains that can then be combusted more easily. But what happens is that if you don't have enough oxygen available, now like so maybe you're near you're like in the part of the flame where there's not enough oxygen, or if the temperature drops or you're running out of fuel or something, what can happen is that any oxygen that there is basically going to be used. So you're going to like strip off hydrogens from this carbon because these carbon hydrogen bonds are weaker than the carbon carbon bonds. So the hydrogens, these will get broken off more easily. And so what you can end up having is that you get water vapor. So you get like water formed, and then because it's hot, then it's vapor. So you have this gas form of water. And then but you don't have enough oxygen for making CO2. So what happens is you actually get these carbon only products. And these carbon only products, because they've lost that like hydrogen, now they have this radical. So they have like a lone electron, and they really don't like having lone electrons. And so what happens is you can get these radical reactions where you have like things with a lone electron reacting with other things and then making those radicals, or react with another radical and getting to like form a new molecule. And so you get all these crazy sorts of like, you have all sorts of weird like rings and all sorts of giant molecules and all sorts of things. Basically this whole heterogeneous like mismatch of different carbon containing products that we basically just call soot. And so this is going to like build up. when you start running out of oxygen and stuff, and this is going to smell. And so this is why the candle starts to smell like when you burn it out and not when it's actually glowing, except if it's like a scented candle or something. But that's when basically the pyrolysis comes in. But then we're going to get actual like chemical reaction induced splitting. And so we're actually going to have this carbon interacting with this oxygen and this combustion reaction. So combustion is like a full oxidation reaction. So we talked a lot about oxidation the other day, but basically oxidation is the loss of electron density, and reduction is the gain of electron density. And we talked about how because oxygen is so hoggy, typically, if you gain a bond to oxygen, then you are going to, we call that being oxidized. You're losing electrons basically because the oxygen is stealing the electrons in that bond. And so for the sake of this post, especially because we can actually see this happening with the oxygen, we can just think of the gain of a bond to oxygen as oxidation, although it's not always involving a bond to oxygen. And then oxidation reduction always has to couple to follow reduction or oxidation, because the thing, something's being oxidized, something else has to get reduced. So basically when we have our oxygen, the oxygen itself, so the oxygen is going to be coming from the air. So our air is like 20% oxygen or so. So when we get and it's in this diatomic form, so it's O2. So you have two oxygen molecules bound to one another. What's going to happen in combustion is that you're going to basically, this oxygen is going to get reduced, so it's going to lose the bonds to oxygen, and this carbons are going to get, and this hydrogen are going to get oxidized, so they're going to gain bonds to oxygen. So when we're talking about oxidation, that's from the perspective of this long like wax molecule. And so we see oxidation a lot in like metabolism, and like especially catabolism, so the breaking down of molecules. So for example, glycolysis, where we're breaking down glucose, we have a bunch of these oxidation reactions that are going to be leading to the formation of ATP. So basically we're taking a molecule, we're taking like a hydrocarbon based molecule and we're breaking it down. And when we're breaking it down, what we're doing is we're going to be generating energy. And when we do it in our bodies, we make it so that we tightly control this energy. So we're actually, with the whole like oxidation reduction thing or whatever, we're going to transfer electrons to these different carriers and then use that to generate ATP, which we can use as a form of like energy storage. So this is a tightly controlled reaction where we are controlling all the energy that it's released in this process. We're capturing it and transferring it and storing it. But what happens in a candle is basically you're just doing it all at once. Well, not all at once, because if you did it all at once, then this whole candle would just like explode. But because you're melting it and like controlling the transfer and stuff, and so you're doing it slowly in terms of like giving it actual fuel. But once you give it fuel, like all this is happening at once, and you're not controlling all of the flow of energy. Instead, this energy is just going to be given off as heat and light. So you wouldn't want this happening in your body, but you do want it happening in a candle. And so basically, you having the light is going to come from a couple different sources. So the yellow light is going to come from something called incandescence. So first of all, like, what is light? So light is basically a form of electromagnetic radiation. So basically, it's just like these like packets of energy called photons that travel in waves. And so we often think about light as being visible light, but that's just like this tiny little portion of this electromagnetic radiation spectrum. And so basically the color of the light is going to correspond to the wavelength. So like how long the wave is in the frequency. So basically all light has to travel at the same speed, the speed of light. So if you have something that is higher energy, it's going to travel up and down and up and down and up and down more times in the same amount of time than something that doesn't have as much energy. So this light that has this higher energy is going to have a higher frequency, and it's going to conversely have a shorter wavelength because it's going to have to, those up and downs and up and downs, it has to do more of them in the same amount of time, and going the same like distance in the same amount of time. So you can think of like a skier or someone running back and back and forth while someone's just like walking. And so basically, if molecules, so if you have this energy being given off in these ways, we call it light. So what happens is that molecules, they can give off light in a couple different ways. So there's one type called like thermal radiation. And so basically, if you have a molecule and it is more energetic than its surroundings, it's going to basically be wiggling a lot, and that wiggling is going to give off some waves. I'm oversimplifying things, but just, yeah, it's going to give off this like radiation. Typically, this radiation is too low of energy for us to see. So it's like in this infrared range. This is why, though, if you have like an infrared detector, like, and you see like on detective shows or whatever, where they're using an infrared detector to try to see where people are, that's because those detectors can detect this light that we can't see. But if molecules get more and more energy, now they're getting pushed into, so we're increasing energy when we go to the left in this diagram. If they get more energy, now they're getting from the infrared range into the visible range. When they get into the visible range, now we might be able to see them. And so this is what happens when you get those molecules really hot. When you get those soot molecules really hot, they're going to start giving off radiation that we can see. They're going to start giving off this like yellowish light. And so we're going to see this. And we're going to see this. This is called incandescence. And this is going to kind of be really, really bright. And it's going to kind of outcompete, I guess, if you will, with our eyes' attention, and hide the blue light. But we'll see the blue light at like the rim and the edges and stuff. The blue light is actually going to involve chemiluminescence. So here, instead of just like the molecules vibrating really fast, here what's actually happening is we're having like electrons being excited and falling down. So remember how we talked about how atoms form molecules by sharing pairs of electrons? Well, if those electrons can exist at different like energy levels. And so they can get like temporarily excited and then fall back down. So they can absorb energy, get excited, and then get released and then give off light. So normally we talk about this when we're thinking about like fluorescence. So that's where you excite the electron using energy from light. So you can shine a light of one wavelength and it'll give off light. It'll give off light of another wavelength. This is super duper useful when you're trying to like label things and track reactions and all that sort of thing. But you can also get this energy coming from things other than light. So you can get this energy coming from like a chemical reaction. And in that case, we call it chemiluminescence. And so this is what's happening to give you your blue light. You have these chemical reactions that are giving exciting electrons, and those electrons are dropping down, and you get this blue light. And you get this blue light because it's more energetic than this other light. So we can see that if we go to the left of this, we're increasing the energy. And so when you get more energetic light, now it starts to be bluer. In order to keep this reaction going, we need to have this like constant source of fuel. And we need to have this we need to kind of get the stuff that's been made out of the way. Thankfully, physics is on our side here. So the convection, so the flame shape, what's actually happening is that the hot gas has energy to move, so it moves. And this is going to lead to, and it's less, so because it's going to move farther apart from one another, it's going to be less dense than the surrounding air, and it's going to move upwards. This is going to give you this convection, where you have this, the movement of air upwards, and it's forming this sort of like flame shape of the candle. So that's going to help get our like made stuff out of the way. But we need to have a constant source of the liquid wax becoming gas wax, and this is where the wick is going to come in helpful. So this wick is typically made out of some sort of like twine, and it's going to be absorbent. And so the melted wax is basically going to get like sucked into the twine, and then through something called capillary action, but basically the wax molecules are going to start like sticking to the twine molecules and getting like pulled up the twine. Kind of like if you stick like a paper towel in water and then you see the water wick all the way through, you're getting something similar, but with the wax wicking through the candle. And then it's going to get into contact with the hotter stuff. And this is going to let it get vaporized into a gas. And once it's in a gas, then it can react with the oxygen. And once it reacts with the oxygen, then it can combust. And if it combusts all the way, then you're going to get water and CO2. And if you only get like partial combustion, then you're going to end up with soot.